Hello, chemistry champion. Welcome to this JAMB session. Today, we are taking on rate of reaction and catalysis, a topic that combines real-world chemistry with mathematical reasoning, and one of that JAMB that has tested every single year for all these years. In just few minutes, you will understand why some reactions are fast and others are slow, and how catalysts speed things up, and how to calculate reaction rates and others mathematically. This is the kind of understanding that separates A-grade students from the rest. Focused, purposeful, let us go. Your JAMB A-grade is few minutes away. Now, what is rate of reaction? What exactly is the rate of a chemical reaction? Simply put, it tells us how fast reactants are consumed or products are formed. Mathematically, rate equals the change in concentration divided by time. The units are mole per dm cube per second, often written as mole per dm cube as you see on the screen. We can measure rate by monitoring gas volume collected over time, watching a balance as mass decreases when gas escapes, observing a color change, or using titration. Quick JAMB calculation: if 0.4 mole per liter of HCl is consumed in 20 seconds, the rate is 0.4 divided by 20, giving 0.02 mole per dm cube per second. Critical JAMB insight is that the rate is always fastest at the very beginning of a reaction when the reactant concentration is highest. As the reaction proceeds and reactants are consumed, the rate decreases. On a concentration versus time graph, the curve gets shallower over time, steepest at t equals to 0, that's time equals to 0, flattening out as reactants run out. Here is the theoretical foundation of everything in this topic: collision theory. The question it answers is, why do some collision produce a reaction while others do not? The theory states that for a reaction to occur, two conditions must both be met simultaneously. First, the colliding molecules must have sufficient kinetic energy. Specifically, their energy must equal or exceed the activation energy, EA. Second, the molecules must collide in the correct orientation. Two molecules with plenty of energy but in the wrong geometry will bounce off each other without reacting. Activation energy, EA, is the minimum energy barrier that must be overcome for the reaction to proceed. Think of it as the height of a hill that the molecule must climb. Only a tiny fraction of all billions of molecular collisions per second are effective, meaning they satisfy both conditions. This is why reactions are not instantaneous even when reactants are mixed. Rate is directly proportional to the frequency of effective collision. Anything that increases the number of energy of effective collisions speeds up the reaction. This is the lens through which we understand all 5 factors affecting reaction rate. Let us start with the factors, beginning with concentration. One of the most tested in JAMB. When you increase the concentration of a reactant, you are placing more particles into the same volume. More particles in the same space means collision happen more frequently per second. More frequent collisions means more effective collisions per second, and therefore a faster reaction rate. Roughly speaking, doubling the concentration of a reactant tends to increase the rate. By how much depends on the order of reaction. For gases, increasing the pressure has exactly the same effect as increasing concentration, because higher pressure forces gas molecules closer together, effectively increasing their concentration in the available volume. JAMB rate law example is that if the rate equals K times concentration of A times concentration of B, doubling A doubles the rate, tripling B triples the rate, and doubling both gives a rate 4 times as fast. The order with respect to each reactant tells you the power relationship. First order means the rate is directly proportional to concentration. Second order means rate varies with square of concentration. Zero order means the rate is completely independent of concentration. These orders must be determined experimentally. You cannot just read them from the balance equation. Temperature is the most powerful factor affecting reaction rate. The Maxwell-Boltzmann distribution explains exactly why. Here is the rule of thumb: for every 10 degrees C rise in temperature, the rate reaction approximately doubles. That is an exponential relationship described mathematically by Arrhenius equation: K equals A times E to the power of negative EA, that's exponential, minus EA over RT. But why does temperature have such a dramatic effect? The Maxwell-Boltzmann distribution graph on screen shows the answer beautifully. The x-axis shows the kinetic energy of molecules, y-axis shows the number of molecules with each energy level. The vertical dashed red line marks the activation energy, EA. At low temperature, the blue curve, the distribution is tall and narrow, with its peak well to the left of EA. Only a small shaded area to the right of the EA line represent molecules with sufficient energy to react. At high temperature, the yellow curve, something dramatic happens. The curve flattens and spreads to the right. Now a much larger fraction of molecules has energy greater than or equal to EA, shown by the larger shaded area. This dramatic increase in the proportion of energetic molecules explain why a temperature increases of just 10 degrees can double the reaction rate. Note that the total area under each curve is the same. The total number of molecules has not changed, only their energy distribution has shifted. This graph is a genuine JAMB favorite. Know it inside out. Surface area, a factor that only applies to solid reactants, gives us another powerful way to control reaction rate. Here is the key insight. Chemical reactions at a solid liquid or solid gas interface can only happen at the surface of the solid. The interior of the surface lump is completely inaccessible to the surrounding reactant. When you grind the lump into a fine powder, you are exposing the interior, creating an enormous increase in the total surface area available for collision. More surface area means more sites where collision can occur, means more effective collisions per second, means faster reaction rate. The classic JAMB example is marble chips versus marble powder reacting with hydrochloric acid. Both samples have the same mass, but the powder reacts dramatically faster. The JAMB real-world applications are fascinating. Coal dust can cause devastating explosion in mines, while solid coal burns relatively slowly. For flour dust in factories has caused explosion for the same reason. Catalytic converters use powdered platinum, palladium, and rhodium to maximize surface area, allowing car exhaust gases to react at low temperatures. The key message when comparing chunks versus powder, the mass is the same, the number of molecules is the same, only the area exposed to the reactant changes. Now we get to one of the most tested and most misunderstood topics in JAMB chemistry, catalyst. A catalyst is a substance that increases the rate of chemical reactions without being permanently consumed or chemically changed. The mechanism is elegant. A catalyst provides an alternative reaction pathway, a different route from reactants to product that has a lower activation energy. Think of it as building a tunnel through the energy hill rather than forcing molecules to climb over the top. With a lower EA barrier, a much larger fraction of molecules has sufficient energy to react at any given temperature, so the rate increases dramatically. Now here comes the JAMB examination critical point, and I want you to memorize this list carefully. What does the catalyst not change? First, it does not change the enthalpy change, delta H. The energy difference between the reactant and product is exactly the same, only the pathway height changes. Second, it does not shift the equilibrium position. The same proportional products and reactant are present at equilibrium. Third, it does not change Kc or Kp. The equilibrium constant is unchanged. Fourth, it is not consumed. The catalyst regenerates itself during the reaction cycle. JAMB will try to catch you claiming a catalyst increases yield or shift equilibrium. It does neither. Catalyst, faster rate, same destination, same amount of product. You can as well watch one of our videos about equilibrium to get more insight about the effect of catalyst on equilibrium. The energy profile diagram is one of the most important visual tools in this particular topic, and JAMB tests it regularly. On screen, you can see two curves. The x-axis is reaction progress and y-axis is energy. The yellow curve shows the uncatalyzed pathway. The reactant starts at a certain energy, climb up to a high peak called the transition state, then descend to the product energy level. The height of the peak above the reactant is the activation energy, EA, the energy barrier. The green dashed curve shows the catalyzed pathway. Reactants and products are at exactly the same energy level as before, but the peak is lower. The catalyst provides a different route with a smaller energy yield to time. Notice three critical things. First, the EA for the catalyte pathway is smaller. More molecules can overcome it. Second, the delta H, the difference between the reactant and the product is identical on both curves. The catalyst does not change thermodynamics, they only change the kinetics. Third, if products are below the reactant level, delta H is negative. It is an exothermic reaction releasing it. If the products are above the reactant level, delta H is positive. That is endothermic absorbing it. JAMB will give you this diagram and ask you to identify EA, delta H, or how catalyst changes the curve. The answer is always catalyst lowers the peak, nothing else changes. Catalysts come in two fundamental types, homogeneous and heterogeneous, and knowing the difference is a JAMB essential. Homogeneous catalysis says that the catalyst is the same phase as the reactant. For example, when sulfuric acid catalyzes esterification, the acid and the alcohol and the carboxylic acid are all in the liquid phase. Nitric oxide gas catalyzes the oxidation of sulfur dioxide in the atmosphere is another example. All gases, same phase. Enzymes in biological systems are homogeneous catalysts when dissolved in aqueous solution alongside their substrate. Heterogeneous catalysis, on the other way, in this case, the catalyst is in different phase from the reactant. The reaction occurs at the surface of the catalyst. Maximizing catalyst surface area is crucial. The four industrial catalysts that JAMB tests most frequently: iron, used in herbal process for ammonia synthesis, nitrogen plus 3 hydrogen plus gives ammonia. Vanadium pentoxide, used in contact process to convert sulfur dioxide to sulfur trioxide, ultimately producing sulfuric acid. Platinum and rhodium gauze, used in the Oswald process for manufacturing nitric acid. What about nickel, used in hydrogenation of vegetable oils to produce solid fats and margarine? All these particular industrial processes were mentioned in one of our videos. You can likewise watch it to get more insight. What about enzyme catalysis? Is the biological equivalent. Enzymes are protein molecules that catalyze specific biochemical reactions. The lock and key model describes how each enzyme fits only its specific substrate. And what is crucial is that enzymes are denatured, permanently inactivated by temperatures above roughly 45 degrees Celsius, and all by extreme pH values. These four industrial catalysts and the enzyme concept, memorize them. They appear in JAMB every year. How do we actually measure the rate of reaction in the laboratory? JAMB tests this practically. Let me walk you through the 6 main methods. One, by gas volume method. Collect the gas produced using an inverted measuring cylinder or gas syringe. Plot volume of gas against time. As the reaction slows down, the curve becomes less steep. Classic example is the marble chip reacting with hydrochloric acid to produce carbon dioxide. What about mass loss method? The reaction flask on a top pan balance and record how the mass decreases as gas escapes. Also great for calcium carbonate reaction. What about titration? Titration removes samples of the reaction mixture at the regular time intervals and quickly quench them, stopping the reaction. We then titrate to find the concentration. This works for any reaction involving a titrable species. Colorimetry here. It is if the reaction involves a color change, like purple permanganate becoming colorless. Use the colorimeter to measure absorbance over time. The clock reactions are beautifully dramatic. Mixed reactant that undergo a sudden visible change after a delay. The longer the time before the change, the slower the rate. The iodine clock reaction, where a colorless solution suddenly turns blue-black with starch, is a JAMB favorite. Graphically, on a concentration versus time curve, the instantaneous rate at any point equals the gradient of the tangent drawn at that point. Rate equals change in y divided by change in z in x. The steepest gradient, the fastest rate, is always at the time 0 and the initial rate. The fastest rate is always at time 0, the initial rate. Now, the most mathematical part of this topic, and JAMB absolutely loves testing this with numbers. The rate law or rate equation is rate equals K times concentration of A to the power of M times B to the power of N. K is the rate constant. It only changes with temperature, not with concentration. M is the order of reaction with respect to A. This tells you how the rate changes when A's concentration changes. N is the order with respect to B. And M plus N gives the overall order of the reaction. For a zero order reaction, the rate is completely independent of concentration. The rate is completely independent of concentration. Changing concentration has no effect. For first order, doubling concentration doubles the rate. For second order, doubling concentration quadruple the rate because 2 square is 4. For third order, doubling concentration 8 times of the rate because of 2 raised to power 3. Let me walk through the JAMB calculation on screen. There are 2 experiments. When concentration of A is 0.1 molar, the rate is 0.02. When A doubles to 0.2 molar, the rate becomes 0.08. Rate ratio 0.8. 0.08 divided by 0.02 equals 4. Concentration ratio 0.2 divided by 0.1 equals 2. And 4 equals 2 to the power n. So n equals to what? 2. So second order, the rate equation is rate equals K times concentration of A square, and K equals 0.02 divided by 0.1 square, which gives 2 mole per dm cube or 2 per mole dm cube per second. The shortcut: compute the rate ratio, compute the concentration ratio. Write rate ratio equals concentration ratio to power n. Solve for n. Now practice time. This question tests one of the most important concepts about catalyst and equilibrium. Read carefully. Catalyst is added to the Haber process. Nitrogen plus 3 molecules of hydrogen in equilibrium with 2 ammonia. Theta H equals to minus 92 kilojoules per mole. Which statement is correct? Just write the answer in the comment section. The answer is D. The catalyst allows equilibrium to be reached faster without changing the yield. Here is why each option is wrong. For option A, catalyst increases yield of ammonia. Wrong. The amount of ammonia at equilibrium is determined by Kc, the equilibrium constant, which only changes with temperature. Catalyst does not touch Kc. Option B, catalyst shifts equilibrium to the right. Wrong. Catalyst lowers the activation energy for both forward and reverse reactions equally. Neither direction gets a preferential advantage. The equilibrium position does not shift. Option C, catalyst increases delta H. Wrong. Delta H is the enthalpy difference between reactants and product. The catalyst changes the pathway, not the start and end points. Delta H is completely unchanged. Option D, correct. The catalyst speed up both directions equally. The system reaches the equilibrium position faster but arrives at the same equilibrium position. In industry, this is enormously valuable. You reach the product yield in less time, using less energy for heating. Did you get it right? Brilliant. If not, you now know the exact reasoning JAMB expects. Now, final practice question, and this is a rate order calculation that JAMB gives regularly in data analysis format. You have 3 experiments, walk through them systematically, and write the answer in the comment section. Yes, the answer is C, third order overall. Here is the step-by-step reasoning. You need to compare experiment 1 and experiment 2, as B is the same in both, 0.1 molar, so concentration of B is not contributing to the difference. A doubles from 0.1 to 0.2 molar. The rate doubles from 0.01 to 0.02. The rate ratio equals 2. Concentration ratio equals 2. 2 equals 2 into power n. So n equals 1. First order in A. Now compare experiment 2 and 3. Concentration of A is the same in both, 0.2 molar. Concentration of B triples from 0.1 to 0.3 molar. Rate ratio equals 0.18 divided by 0.0 and equals to 9. Concentration ratio equals 3. 9 equals 3 to the power of n. Since 3 squared equals 9, N equals 2. Second order in B. Rate equals K times concentration of A times concentration of B square. Overall order 1 plus 2 equals 3. The third order overall to the first to find K from the experiment. 0.01 equals K times 0.1 times 0.1 square equals K times 0.001. So K equals 10 per mole square. dm is for 6 per centimeter per second. The golden method always picks two experiments where only one variable changes, isolate each reactant order separately. Overall order, that method works every time. And here is your complete rates of reaction and catalysis cheat sheet. Everything you need in one beautiful table. Screenshot this right now and save it, and for your revision, share it with your study group. They will thank you. 5 factors: concentration, temperature, surface area, catalyst, and pressure, all increasing the rate. All explained by collision theory. 4 industrial catalysts: iron for Haber, vanadium pentoxide for contact, platinum for Oswald, nickel for hydrogenation. Rate law: rate equals the concentration of B to the N. Overall order equals N plus N. Concentration doubles, rate doubles equals first order. Concentration doubles, rate quadruple, that's second order. You have covered everything JAMB has ever tested in this topic in few minutes, and it's incredible. Here is what I need you to do right now. Like this video. It takes 1 second and help thousands of others JAMB students to find this content. Subscribe and ring the notification bell so you can never miss this with your WhatsApp study group, your classmates, your school friends, and comment below. Or rate law calculations. I want to know. Stay tuned. Chemical equilibrium and the Catalysis principle is always there. Is there on the every mark you score in JAMB is built on preparation exactly like this. Your grade is not wishful thinking. It is inevitable result of this kind of focused, consistent revision. Move case.